Hello, this is me working out the key to Force Quiz 1, given on October 27 and 28, 2020. So the first one, and of course I shouldn't say the first one because you're maybe in a different order. But anyway, we had one where Sam weighed 714 newtons on Earth. And he goes to a different planet where he has a different weight. So we know the gravitational acceleration on that planet is going to be different. So instead of calling it G, I'm going to call it G prime. Prime is just an apostrophe. It's just a way of saying, hey, this is a different G. It doesn't mean anything in particular, just that it's different. Okay, so first thing I'm going to do is figure out Sam's mass because mass is the same everywhere. So weight divided by G. So you're going to put in Sam's weight right there, okay? And then divide by G and you'll get his mass in kilograms. Now, I want to find G on the other planet. So if you look at this equation, you can just do the finger flip on it, right? So whatever his weight is there, divided by mass, because M and G are trading places, that's going to give you how much G is on that planet. So I'm going to put a blank box here because that varied from person to person or test to test. Sorry, quiz to quiz. But I'm going to divide in each case by his actual mass, right, on Earth. And so when you do that, in this case, you put in 1,325, because on this version of the quiz, that was his new weight on the new planet, and you get a G of 18 meters per second squared. Okay, so choose the right one, and you're all set. Second question, I have a net force that accelerates a tool, and then I'm asked, what acceleration would the same force give to something with a different mass? So just like the last problem, I'm going to have two steps. So the first thing I'm going to do is figure out just how much force that is. So I put in the mass of the tool times the acceleration, and this varied from test or quiz to quiz. So in this case, it was 3.68 times 27 meters per second. So now I know how much force we're talking about. So to find the acceleration of a different object, acceleration is going to be force divided by mass, right? The net force divided by the total mass. Well, I only have one here, so it's pretty straightforward. So this is where I put in my 99.36, because that's what this version gave, and I divide by the new mass of the new tool. So that's 5.32 kilograms on this particular version, and so I get 18.7-ish meters per second squared, and you choose that from the list. A third problem for us is that somebody is pulling something where there is friction between the two surfaces, and they want to know the acceleration of the object. So I can start off with the free body diagram if I want to, and come up with a net force statement if I want to. I can just immediately jump to rearranging it for Newton's second law if I want to, because this is multiple choice after all. So the net force statement would be friction to the left, so it has a negative sign, and the pull to the right, so it has a positive sign, and then I'm going to divide by the mass. I wasn't given the mass, I was just given the weight. Okay, so I'm going to go for it. So in that box goes whatever your version had. This particular version had negative 38 newtons because it was 38 newtons of friction to the left. So when I put that in and I divide by the mass, I get, in this particular case, 0.9408 meters per second squared, and I choose the closest number from the list. Turning to another page. This one looks scary. It looks like it's an Atwood problem or something more complicated, you know, than you were expecting, but it's not, okay? So we have nothing sideways affecting the up and down here. There's no friction up there. There are no forces up there at all. What I have is something that's going to fall, okay? So the force on it is going to be its own weight. So I have to realize, first of all, that weight is the force that I'm after. So when I have that, I also need to think about sluggishness, because net force divided by mass is what gives us acceleration. So only the dangling weight is the unbalanced weight, right? The weight of the block on the table has the normal force lifting it, so it's really not an issue for us at all. And the mass is going to be increased by not only the mass of the object that's dangling, but the 10 kilograms of sluggishness that it also has to tow. You want to think of it that way. So this was maybe the hardest problem on the test. But what I'm getting at, you know, is this independence of these vectors and the fact that weight has got to pull on two masses. So it's sort of like our very first problem on the first page of force packet 2. That is, we're looking at systems of masses. I'm going to think about it as a total mass, a single mass. But weight's only pulling on part of it. Okay, so I put in my mg. In this case, my mass is 53 for the dangling block. So the total sluggishness is going to be the 10 kilograms it's dragging with it, plus the 53 that's falling. And I've got 8.244 meters per second squared on my calculator here. So that was your challenge problem. That was a hard one. Okay, here we go. An object slides on a level floor. Oh, okay, it comes to a stop. So this is like the one we had in our notes in Force Packet 1. So I have normal up and weight down, and I can mostly ignore those because I know they're going to be balanced. I have no force required at all to make something move forward. It already is moving forward. So what I have is an unbalanced frictional force, and that's why it's slowing to a stop. So sum of all forces is a very short list. It's just this friction. You can make it negative if you want to. That's a good idea here. But anyway, mass times acceleration is mu times the normal force. Now, these two things are balanced, I know, because it's not punching through the floor or flying up in the air. It's on a horizontal surface. So I can substitute one more time, just like we did in our notes, and put in mg. When you do that substitutions, you can see that mass doesn't matter. So I have the acceleration is mu times g in magnitude. Well, in this case, I'm asked to find mu. So to find mu, I'm just going to divide both sides by g. Okay? And when I do that, g will cancel out here and show up over there. So I have mu, positive or negative, however you want to look at it, is a over g. Okay? So in this case, I put in didn't leave myself enough room, did I? 3.28 meters per second squared, and I divide by 9.8. I can make it negative if I want to, and there I have my acceleration. It just says magnitude, so that's why I'm saying it doesn't really matter what sign you have. So I'm looking for a 0.33, and there it is. Okay? A truck. When a truck collides with a smaller car, which one experiences more force? They both experience the same. This was a Newton's third law problem. If you clap your hands together, you cannot have one hand hit hard and the other hand hit soft. It's either soft for both of them or hard for both of them. Try hitting both hands together and see which one stings. They both do. Try to hit one and the other hand moves away. There's no force at all. You can't have one force. They come in pairs. Okay. So during the collision, the force on the truck is equal to the force on the car. Pretty wild, huh? It's true. Okay, a person who normally weighs 700 newtons is riding an elevator moving at a constant speed. Isaac Newton said, if you want to know about force, watch for acceleration. Acceleration is 0. So if I see the words constant speed in a problem, those are magic words. They're probably going to make my life easier. Okay. So when I think about a person, I have the force reading on the scale, Fs, and I have the weight, W. Okay. And so mass times acceleration, the net force, is going to equal the force of the scale up and the weight down. And since I've just learned that this is 0 by reading the problem, the force on the scale is going to exactly equal that person's weight. In other words, the bathroom scale is going to work just like it should. Okay? So that person has their true weight appearing on the scale, whether they're moving up or down. They are moving at constant velocity. Acceleration is 0. Here's something else with acceleration equal to 0. You had a problem with a person picking up a box. So if you try to pick up that crate, think about the forces on it. There's going to be a lifting force, right? So that can be the pull. She's pulling upward because it says upward pull. And then I also have the normal force, right? Coming from the floor, going on up. So I have a normal force. And then I also have weight straight down in the center of the earth. So I have 2 ups and a down. What do I know about those things if the crate doesn't move? She's trying unsuccessfully. It says without success, it doesn't move. Well, that means the sum of all my forces, my mass times acceleration, is going to be 0, isn't it? So 0 for a P up, a normal up, and a weight down. That means the weight force, if I add it to both sides, is being balanced by those two working together. So I look for that in my choices, and it is there. Okay. Now, here we have a tow truck problem and some algebra with a hint about how to use it. So in this case, I have the maximum force of the tow truck. So whether it's, revving its engine and just driving itself, or it's pulling something, I have one force in either situation. So mass times acceleration is going to be mass times acceleration. But if I change the mass, I'll change the acceleration. So there I am using that apostrophe again that I pronounce as prime. So that's mass prime, acceleration prime. In other words, it's like new mass, new acceleration. Okay. So in this case, I had a bus that was 3 times the mass of the truck. So when I look at total mass here, I have the mass of the truck plus 3m for the bus. So therefore, the total mass is going to be 4m. So my new mass is 4m. When the truck was all by itself, it was just m. So all by itself, the truck had an acceleration of 6, okay? But now it's 4m with the same force. What acceleration results? Well, you can see here, I think, why I don't like us putting units in. I put that in just so you could look at it. See how messy that m is? I don't want to see that meters per second squared. So I want to focus instead on the fact that this mass and this mass divide away. So all I have is 6 is equal to 4a. So that means a prime, sorry. So that means a prime is 6 divided by 4, or 1.5. And now you can go ahead and put in the meters per second squared. So you find that on the list, and choose it, and you solve that problem also. One more to go, here we go. In this case, you had a mass that was traveling. So it's a car, and you've got an original velocity, and it slows to a stop. Okay, so I also know how far a distance it goes. And this is actually something that varied between the different versions of this quiz. So I'm going to use the VF squared equation because I'd like to get the acceleration and I don't have time. So that looks like a great way to go because I'm supposed to come up with force over here. So let's go for mass times acceleration by first solving for acceleration. So final squared minus original squared divided by 2 times the displacement. So 24 squared divided by 2 times whatever your displacement was. In this case, it was 458 meters. So I calculate an acceleration. It's negative, and that makes sense for something coming to a stop. So this is negative 0.62 something meters per second squared. So now I'm going to go to F is equal to ma. I'm going to go back to the problem and pull out the mass. So there's the mass of the car times the acceleration. It would take that much force to give that car that much acceleration. Okay? So there's my average braking force. It says magnitudes. It doesn't matter if it's positive or negative. And I choose that closest number from my list, 692. Okay? So there's a lot of Newton's laws on that, wasn't there? That's really what it's all about. I mean, if you think about it, how many equations could you have written down? Like if we'd had an index card, what would you put on there? F is equal to ma. A is equal to F over m. It's really very much Isaac Newton's principles in Principia that are guiding what we understand about force. All right, so there's your key. Remember, you can replay this. You can also put a blank piece of paper on top of your quiz like that. Solve again any problem that you missed, and then come back and play this key to check your work. Bye-bye.